All right, thanks everybody for coming, and thanks to Tej Chajed for coming to give us a talk. It's nice that many of you are able to come attend this. He is a systems student working on formal verification of software at MIT, advised by Franz Koschek and Nikolai Zeldovich. There's still some space on his schedule. If later this afternoon you'd like to talk to him, come to me and I will arrange a spot on his schedule. So let's hear from Tej.
Thanks, Jay. So to motivate why we're talking about layered storage systems, let me start with a story. So the story will tragically lack modularity, but then Argosy will come in and fix that. The story starts with Bob, a storage system developer who's writing a replication system. The replication system takes two disks that are unreliable, and it exports a single logical disk with reliability. The way it works is, as writes come in, it writes them to both disks, and that ensures that your data is safe even if one of these disks fails. Now, this is a storage system, so Bob wants it to be able to handle crashes at any time, say due to a power failure. And the problem is that if the system crashes in the middle of a write operation, then it leaves the disks in an inconsistent state. So Bob knows how to handle this. He writes a recovery procedure that copies from the first disk to the second, and that restores the invariance of the system. Now, Bob is a careful guy, so he writes a machine-checked proof of correctness that his code is correct. Specifically, that read and write are atomic and have the right behavior, as long as you run rep recover after every crash. And because he's using the latest verification infrastructure, his proof handles crashes during recovery itself. Meanwhile, Alice writes a write-ahead logging system that implements a transactional API on top of a single disk. And she also proves her code correct with the machine-checked proof of correctness with this log recovery procedure. Now, you look at this picture, and you think, surely we can run the write-ahead log on top of the disk replication system, and we can prove that composed implementation correct. The trouble is that the recovery procedure to make this code correct needs to run both of the underlying recoveries. And it turns out that this is tricky to reason about formally. So you have a proof we have a proof that each of these recovery procedures is correct in isolation, including crashes during recovery. Crashes during the composed recovery procedure don't directly resemble crashes during either of the sub-recoveries. So the challenge is, how do we actually reuse these proofs? And prior work, it turns out, can't do this. So Crash Hoare Logic, our own work from a verified file system, has no way to move from a proof about one recovery procedure to a proof about another. You can only have one recovery procedure at a time. Yggdrasil, similarly, has no metatheory for composing two recovery procedures. It sort of implicitly assumes a global recovery procedure. And FlashX, while they do support composition, they place some restrictions on recovery procedures to make that proof go through, and it disallows both of these systems. This is where Argosy comes in. Argosy supports modular proofs that support exactly the style that we wanted here, where two developers independently prove two implementations correct, and there's a generic theorem that the composition is correct, including crashes during recovery. And Argosy is compatible with existing techniques, so we re-implemented Crash Hoare Logic for the sake of this work in order to prove the implementation is correct individually. OK, so the main contribution in this work is recovery refinement, which is the approach that we use to get modular proofs. And I'll also talk, if I have time, about Crash Hoare Logic, which is how we connect Argosy to Crash Hoare Logic to prove a particular implementation correct. And see the paper for details on an example that we verified featuring write-ahead logging on top of replication, the same example I've been using. And all of our code is backed by machine-checked proofs in the Coq proof assistant. OK, so, and sorry, I should say that if you want to interrupt me at any time, feel free. If you have questions, don't wait till the end. So let me go into recovery refinement next. To explain recovery refinement, I'll do so in two steps. First, I'll talk about just some background on how to prove normal execution correctness using refinement. And then next, I'll talk about how to extend refinement with notions of crash and recovery to arrive at recovery refinement. OK, so here's some background on refinement before we get into recovery refinement. In refinement, the goal is to prove that an implementation correctly implements some exported interface, say this single disk in the case of replication, on top of some code interface that the code is written against, in this case, these two unreliable disks. The replication system implements every high-level operation, say a write, in terms of the low-level operations. In this case, the write implementation just writes to both disks in turn. And similarly for the other operations in the interface. So what does it mean for this replication system to be correct? We define correctness based on how you would use the replication system. Specifically, you'd take some piece of code and you'd write it against the disk interface. And what you want to know is that when you run this code on top of 2 disks using the replication system, it behaves the right way. It behaves the way you expect. The way we formalize that is the standard idea of trace inclusion, where the specifications behaviors at the disk layer should include all of the running code behaviors at the 2 disk layer. So that's just normal execution. But how do we prove this property correct? The way we do that is using an abstraction relation. This whole technique is also called forward simulation. This is all still standard stuff, still background. So with a forward simulation, the developer provides an abstraction relation R, which has 2 purposes. First, it relates the states of the specification to the states of the code. And also, it enforces any invariance over the code. So in this case, the replication system maintains this invariant that the 2 disks are equal. Then the developer proves that for every execution of the code, there's a corresponding execution of the specification that preserves the abstraction relation. And that lets you run more pieces of code after this operation. And to get the full trace inclusion property, the developer just needs to prove this for every operation in the system. OK, so that's all the background I have on refinement. Now we'll extend all these notions with crashes and recovery, which is the new part of this paper. So here is the picture that we had for an implementation. Now we'll extend this with crashes and recovery. Recovery just goes into the implementation, but I've also added these power symbols to both interfaces. These power symbols represent the semantics of what happens on crash. For example, volatile state is cleared. Your memory is wiped. Anything that's in, say, buffered in your disk goes away. So that just handles the specification. That just handles modeling crashes and recovery. What about the correctness for recovery? We still use trace inclusion, but we'll extend it with notions of crashes and recovery. And to do that, I'll introduce our crash semantics to describe the specification, and then the recovery semantics to describe what code we actually run. The crash semantics that we use is intuitively it's atomicity. And the way we formalize that is you can crash before or after, between any pair of atomic operations. And standard assumptions for what's atomic are things like 4 kilobyte writes or file system operations you might assume are atomic with respect to crashes. And I'll represent a crash in the middle of a piece of code between any atomic operations with this jagged edge followed by a power symbol. So that handles the specification. What about the code? We're definitely going to run recovery after a crash in the middle of the implementation. We know that the code needs to do that. But we also want to model crashes during recovery, so we insert 0 or more iterations of crashes during recovery first. And that's all we need to specify what trace inclusion with recovery is. It's normal execution plus correctness under crashes and recovery. How would we prove this property? We're still going to use an idea that's like forward simulation, but let me introduce how we come to the right condition. So the first observation we make is that if you crash in the middle of some long sequence of code, you must crash in the middle of some operation. And in this example execution, that crash occurs in the middle of op2. And prior to that crash, you can just use normal execution correctness to establish that the abstraction relation is preserved up to that point. So we can sort of ignore that, because normal execution correctness will already handle that. What's the specification for a crash during op2? We said it's atomicity, so we simply use either all of op2 occurred and then the system crashed, or none of op2 ran and the system crashed. And that condition for all the operations is all we need for recovery refinement. So we still have normal execution correctness for non-crash execution, and then we also have this new condition that relates recovery to crashes. And proving this for every operation in the system is sufficient to prove this strong trace inclusion property for running arbitrary pieces of code against the top-level interface. OK, so what I've talked about so far only handles a single layer, but this talk was supposed to be about layered storage systems. Sorry, go ahead. Yeah.
Why does the specification have to have a notion of crashing at all? Shouldn't crashes be invisible in the specification?
Yeah, that's a good question. So many systems would try to hide crashes, but we also want to reason about systems like file systems that cannot hide crashes from the caller. Just fundamentally, if you're running a code on top of a file system and you crash, something will be lost, or at least we're going to lose track of what you were doing. So we want to be able to give these weaker specifications. If you go off and you write some large distributed system, you'll probably try to hide crashes. Basically, you need to replicate for that to work.
What properties do you say about the relation R? In a way, if I want to reason about a low-level system, I would like to reason about it through the abstraction of the high-level system.
Yeah.
And R is my interface to do that.
So our specification does not have R. So the specification should be that, okay, so there's a distinction between, so R is talking about states. The states are just helpful to specify what the behavior of a piece of code is. But once you get to the specification, you only need to look at the interface and the externally visible behaviors, which in our system are return values. But a natural extension is things like the network packets that you send out. Then you don't need to worry about how R works.
If I prove a property about a high-level trace,
Yeah.
and I want to conclude something about a low-level trace,
Yes.
you have to somehow transport my property across R, right?
So ideally, your property should only be about, it should not be about states. It should only be about return values. And if there is something else that you care about, you should externalize it as I/O behavior of some sort. The intermediate states should be irrelevant. I mean, that's the intention of the system. I didn't talk about this, but you do need to establish R initially as well, right? It's an inductive invariant, and you need a base case. It's just generally not interesting. But if you don't do that, then you would need to look at R. You would need to look closely at R to make sure that it's actually satisfiable. Okay, so next I'll talk about the composition theorem that lets us actually take two recovery refinements and compose them together for modularity. Before I do that, let me talk about Kleene algebra, which is the approach that we actually use to prove the composition theorem. So I've been using these expressions informally in the talk, this alternation symbol and the star. It turns out that these are exactly the operators of Kleene algebra, which is a formalism that generalizes regular expressions. So you can use basically all of your intuition from regular expressions to think about these operators. We don't just have these informally, we give them a formal meaning in terms of matching transitions of the system. So sequencing corresponds to sequencing of transitions. This alternation symbol is non-deterministic choice between two possibilities. And the star is 0 or more iterations. And if you look, you'll see that these are exactly the operators that we needed to define the semantics of crashes and recovery. So Kleene algebra is quite closely, it seems like a good formalism to at least model what's going on. But it's actually also useful for reasoning principles. Kleene algebra has a rich theory for when two expressions are equal. And I'll talk about that theory in a bit when I go into the composition terms proof. Okay, so let me just formalize what the modularity that we get is. Now that we have recovery refinement, I can more precisely state what composition is. If we have two recovery refinements that are stacked like this, then Argosy has a theorem that says that the composed implementation is also a recovery refinement, and therefore has this trace inclusion property, where that composition needs to run both recovery procedures. Okay, so before we said we had this challenge of how do we get a proof about the composed recovery from both individual recoveries. Now I can formalize a little bit more how we might go about doing this reasoning. Before I do that, let me just abbreviate these two with rep for the replication system and log for the logging system, just to keep the slides a little less cluttered. Okay, so now we can formalize what we mean at least by under crashes. It's 0 or more iterations of crashes during recovery before recovery finally finishes. Here's an expression that represents crashes during the composed recovery. And just to break this down a little bit, it starts with either we could crash during the replication system itself, or the replication system might fully recover, but then we crash during the logging recovery. There's some number of iterations of crashes during recovery, and finally the system stops crashing and the whole composed recovery runs. Okay, so this doesn't seem any easier. The top two expressions don't show up in the bottom expression, but Kleene algebra can fix that. Okay, so Kleene algebra has, as I said, it has an equational theory that lets us rewrite these expressions to equivalent ones. So the first theorem we apply is a theorem called denesting, which will let us get rid of this alternation altogether. Next, we apply a theorem called sliding. And this might not seem simpler, but I'll go through why this bottom expression is easier to reason about. Kleene algebra has told us that it's exactly equivalent to the original in terms of it matches exactly the same transitions. Okay, so after this rewrite, both of these proofs sort of start to apply. Before the parentheses, the replication proof establishes that the recovery procedure restores the invariance of that system. And then within the parentheses, the trace inclusion property for the replication system says this behaves like a crash during the high-level logging recovery code, where from the perspective of the replication system, log recovery is just another program that you wanted to run. So that's all we need from the replication proof. Then we can take what we now know and plug it into the write-ahead logging proof, which shows that the logging system correctly restores the logging system's recovery correctly restores its invariance. And the upshot is that at the end of this composed recovery, despite crashes during recovery, both systems' invariance are restored. So I've talked about this in terms of informally restoring invariance, but the paper and especially the code formalize this more precisely as recovery refinement. And let me just give a small flavor of how not only is Kleene algebra useful for equational reasoning, just rewriting expressions to equivalent ones, it also actually lets us do refinement reasoning. So this little refinement diagram, this is like the standard one that we've been using in this talk, you can encode this as an expression in Kleene algebra, as a subset relationship between two possible transitions. There's just one thing slightly weird going on in this expression, which is that we sort of run R as if it were a program. Much like a program, R is also a relation between states. And then that subset is just another operator in Kleene algebra that says that one regular expression matches a subset of what another regular expression matches. And Kleene algebra also has a theory for reasoning about these subset relationships. OK, so that was a lot of abstract description of composition. Let me just go back and motivate why you might want this sort of modularity with a real example from our work. So here's an anecdote about where modularity failed us in some prior work that we did. So we wrote this verified file system called FSCQ, and in one of those papers, we wanted to prove some application correct on top of the specification, and that job fell to Franz, my advisor. So Franz wanted to prove this little snippet of code correct. It's not super important what it does. All it's trying to do is atomically save a file by first going through a temp file. And he wanted to prove that this is atomic. To make it atomic, we need to run this application-specific recovery procedure that cleans up the temp file on crash. And it turns out that this code took a 1,500-line proof because of this little FS recover that's hiding in the application recovery procedure. So as I said, Crash Hoare Logic has no way to move from a proof about one recovery procedure. In this case, the whole system is proven with FS recover as the global recovery procedure. Now we need to move to a proof that has this recovery procedure with one extra line of code. And proving that this is correct basically required inlining the entire proof, redoing the entire proof that FS recover handles crashes during recovery, FS recover is correct when composed with unlink, and that this entire procedure is the correct thing for atomic save. So we didn't redo a file system, but in Argosy, this should have been completely trivial because you don't even observe the lower levels recovery procedure when you're reasoning about atomic save. OK, so the story so far has had recovery refinement. And from recovery refinement, we've gotten two properties, correctness in the sense of trace inclusion, and also modularity because of the composition theorem. But I haven't talked about how you'd actually establish a recovery refinement in the first place, given just a program. This is where Crash Hoare Logic comes in. So Crash Hoare Logic is the program logic from FSCQ, which lets us reason about crashes during code as well as during recovery. So I'll describe Crash Hoare Logic, which is mostly prior work, but then it'll connect back to Argosy. First, I'll just give a very brief overview of Hoare Logic in one slide. So the basis of Hoare Logic is this statement called a Hoare triple, which it's called a triple because it has three parts, a precondition, a postcondition, and a piece of code. And the interpretation of this Hoare triple is that if you run the code in a state satisfying P, and it terminates, then the resulting state will satisfy Q. So Crash Hoare Logic is just an extension of Hoare Logic, where instead of writing Hoare triples, we write these crash specifications that describe what happens on crash. We have an extra sort of an extra postcondition, which is a crash invariant, which will hold following a crash at any time during this piece of code. So that's just crash specifications, but we also want to reason about recovery. So Crash Hoare Logic has another statement called a recovery specification that it has, instead of just a piece of code, it also has a recovery procedure that you intend to run. And it describes what happens if you crash in the middle of the piece of in this code and you run recovery, including crashes during recovery. So here I've just baked crashes during recovery into the definition. That doesn't help us prove this correct. So these crash specifications are pretty easy to reason about because they chain nicely. If you crash in the beginning or the end, the new crash invariant is going to just be the OR of the two crash invariants. these don't compose nicely at all. So how do we actually prove these things correct? So for that, basically, in FSCQ and again in Argosy, we prove a theorem that lets us establish these from just crash specifications. So let me show you what that theorem looks like sort of diagrammatically. So first, you write some crash spec for the code, and pre and post conditions just chain as expected, because that's just normal execution and recovery doesn't even come into the picture. Then you prove a crash specification for recovery. And the interesting thing about this specification is it should be idempotent, meaning that crashes during recovery should imply the precondition for recovery. Intuitively, this is what you want, because if you crash during recovery, you're going to need to rerun recovery. Then we just need to chain these two together, so when you crash in the middle of the code, you're going to go into this recovery crash loop, and then finally, when you stop crashing, we'll get this post-rec condition. Yeah. And all we really had to do in Argosy is connect Crash Hoare Logic to recovery refinement. We still need an abstraction relation. And then all we actually need is to prove a particular Crash Hoare Logic recovery specification using the standard techniques of Crash Hoare Logic. And these will encode recovery refinement. And I'll just show that graphically. Oh, there's a build error. OK, so the precondition is the precondition for both of these refinement diagrams, that there should exist some abstract state satisfying R. R is sort of also a precondition. And then the postcondition is the normal execution part of recovery refinement, while the recovery postcondition is the crash and recovery part. And I've de-emphasized these lower left parts because they're actually baked into the definition of what this recovery specification means. I'll skip this. OK. So while this Crash Hoare Logic part of Argosy is fairly standard, it does complete the picture. It actually lets us prove programs correct. In particular, Argosy, Crash Hoare Logic is what lets us reason about crashes during recovery for logging and for replication separately. OK, so we didn't just write a paper on this. We also implemented and verified all of this in the Coq Proof Assistant. Our framework is fairly small as far as our systems go. It's only about 3,200 lines of code for the generic theory. By contrast, and our example on top of that is 4,000 lines. By contrast, FSCQ was like 40,000 lines of code, of which 20,000 was the framework. And this example does extract to Haskell and run. And our code is open source. Let me briefly talk a little bit about some directions for future work that we're actively working on now. So the first is the big limitation of Argosy is that it's sequential. It only supports sequential storage systems. So we're now working on a story for crash safety combined with concurrency. The way we're doing that is instead of extending Argosy, we're instead taking the ideas from Argosy and extending an existing existing concurrency infrastructure. It's based on concurrent separation logic, a very old idea, but a modern instantiation of it in a framework called Iris. Iris has been used successfully for a lot of concurrency projects with a long line of POPL papers establishing the framework and then many more papers with applications. But we're the first to come up with crash safety techniques for Iris. We also want a better story for running code. So currently in many of our systems, I've extracted to Haskell, and this gets us a lot of performance problems. I don't want to be too down on Haskell, but we lack control in this workflow because we can't really control what the extracted code looks like and get good performance out of Haskell, especially when trying to get high performance for concurrency. One of the things you need to do, for example, is reduce memory allocations, which is quite hard to do. And our new plan is instead to import Go into Coq, which I'm very excited about. This is a very fun thing to do. Another thing that we're doing is we are subjecting students to this. Oh, yeah.
Yeah.
Sure. I was like half ready to just give a separate presentation on this, but I'm happy to chat about this offline. So it's not OK. So it's a completely trusted pipeline where I basically wrote a small translator to translate a small subset of Go into Coq instead of going the other way around. So we translate Go programs into some model in Coq.
So you have an Iris semantics of Go?
Essentially, yes. So Iris is actually fairly general. So Iris doesn't really come into the picture of the specification, but we have a transition relation that describes all the operations that we care about from Go. So heap operations and file system operations, because we need to use the file system.
Do you have a deep embedding of Go with some sort of dedicated model for library operations related to the file system?
Yeah, it's not quite deep. We translate into our standard representation of programs, which is a shallow embedding. Okay, so we will in the coming fall semester, we will subject students to this, including Sydney, actually. So Argosy actually spun off from course infrastructure, and now we want to backport the improvements in Argosy back to that course infrastructure. And for the sake of students, we basically need to make the Crash Hoare Logic part more usable, and make sure that this whole infrastructure is a little bit easier to use. Okay, so to summarize, I've talked about Argosy, which gives us modular proofs of layered storage systems. It appeals to Kleene algebra, both to model crashes and recovery, as well as for principles to reason about the composition theorem as well as correctness. We've introduced recovery refinement, which is the approach that we use to get all of these nice features, and that it gives us the right conditions to establish trace inclusion for recovery. And finally, I've talked about how recovery refinement also gives us modular proofs. It lets us compose implementations together. Thanks, and I'm happy to take more questions. Yeah.
When you talked about the compositionality using this Kleene algebra, you ended up with this big expression, and one of the things it said was like the logging system runs and crashes, and then
yeah, I can find it.
Replication runs and crashes.
Yes, this.
Yeah, and then you said, well, that thing behaves like something simpler.
Yeah.
So how hard is it to do that proof? And when do you have to do that proof?
So this is I've instantiated this example with rep and log with these two systems, but we did a single composition theorem for two generic layers without ever looking at what the layers actually do internally.
Okay, so that behaves like conclusion there works for everything then.
Yes,
okay.
Yes. That's something that you would have to prove if that's something that you get from the fact that the system is a recovery refinement. That's the only assumption that we make.
Can you give some intuition for why that refinement is true? You just
okay, so
the replication part completely.
Yeah. It's because there's a small pun which is not great of this example. So that top part is not the thing that's being refined is this is the logging recovery procedure compiled down to run on top of the two disk interfaces using the replication system. Right, so before I said that like code impl followed by crashes during recovery refines the high-level code at the upper layer. So what the refinement is establishing is that the log recovery procedure at the replication layer behaves like the log recovery procedure at the disk layer. Yeah. Yeah.
You know, for the you showed this bit of sample code that Frank had to write.
Franz, that Franz proved.
And in Argosy, would they have to write it differently? Like, would they have to use FS recover at all?
No, you would not. Sorry, let me find this slide. So you would express atomic copy either as... So you would probably express this atomic copy example as a layer that has one operation, atomic save. Maybe you'd also re-export all the file system operations. And then your recovery procedure would not be able to mention FS recover. Right. It would be added in the process of combining with the file system.
Cool.
Also, another thing you'd get for free is that unlink would become an atomic operation, whereas this unlink call is actually a call to a bunch of disk operations. Because in FSCQ, like everything is written against a disk API. There is no layering.
One more question.
Yeah.
I'm curious about in practice, what invariants you can use as the invariant of a recovery procedure.
Oh, yeah. Like the crash invariant that is invariant under...
You have this invariant that to get item potency, you require an invariant. I'm wondering in practice what invariants you have.
Yeah, so the replication system, it's fairly simple. I think... So there's sort of a standard trick, which is if I were to finish recovery now, it would be correct. That's sort of like a standard invariant. That's sort of the standard way to think about what the invariant says. That's like an always true statement. In the case of the replication system, because this is a sequential system and everything is stable right away, if you crash, you can only ever crash in the middle of one write operation. So the invariant is either the disks are fully synchronized or they're desynchronized at one point. And recovery basically finds that point in a loop. In the logging example, it's a little bit more complicated. But similarly, if you crash, we can basically ignore whatever progress was made so far. Because actually, in reality, we're going to redo it. That's because we do physical logging, so it's fairly simple. There's also like undo redo logging, which is more complicated, where if you crash, you actually need to undo what you did during recovery. But I think similarly, you'd use this idea that if I were to finish now, I'd be OK. And you just prove that that's true for even the things that you've done right now. So done so far.
Does this exclude things like, have arbitrary corruption on my disk? That from what you were saying, you defer only on at most one location that you're trying to find and fix up, right?
Yeah.
But
So so I have another
just totally trash my drive by, throwing a bunch of, magnets or cosmic rays in it or whatever.
Yeah.
Right. Then this may not be true, right?
Yeah. So in the replication system, we have a model of how it's unreliable. The model says that at any time, one of the disks might go away entirely. And then from then on, reads will fail when you try to read from that disk. So if a disk fails, then actually the disks are now synchronized, and so we can return. We have to make this assumption that only one disk can fail, because if both disks fail, then clearly you're screwed. I think this is actually like a big difficulty in proving replication systems correct, is they're not unconditionally correct. You have to rely on some assumption.
Any more questions? All right, let's thank Tej.